já cá ficaram. Eu estou socialmente a sala mais invejada do Cdays. Para mim é ótimo. Esperemos que para o ano a sala ainda aumente mais um bocadinho. Para o salão já está a perceber os que têm invejado. Vamos ter agora o Tiago Carvalho. Eu já tive o prazer de ver esta apresentação por 2 vezes. É um conceito bastante interessante. O Tiago irá explicar. Como está ali o password profile. O Tiago é representante da Cdays aqui no Cdays. Para quem não esteve cá ontem, a Cdays é uma comunidade de segurança, principalmente em Lisboa, mas na área dos estudantes de Lisboa, onde promove confraria e não só. Está muito ligada também ao Insights em Lisboa. E tem a responsabilidade de promover a segurança informática em Portugal. O Tiago criou o seu primeiro jogo em Basic, com 9 anos. Trabalhou durante 8 anos como programador de Java. Tem uma curiosidade muito interessante, é que foi o coautor do primeiro sensor de manobras de BMX e é atualmente analista de segurança, portanto, testa de optimise. Vai apresentar aqui uma metodologia de encontrar passwords de uma forma muito mais rápida. Esperamos que gostem.
Thank you. So, this part already talked about. So, we're talking about password profiling. Essentially, what we're talking about here is how to answer a few questions I read about a few months ago when I started researching the concept of hash cracking and the time behind all the permutations that we need to solve when we're trying to crack a hash or someone else's password. So essentially, we're dealing to try to figure out a good way or efficient word list, or to choose an efficient word list, how to tackle the word list generators problem, choose how we're going to generate these word lists, and eventually do a few tweaks here and there to improve the time required to crack someone's password. So essentially, we're trying to answer these issues. The blind brute force takes a lot of time. We'll go over this, what this means in a short. Choosing the best word list is also important. The number of permutations, what they are, how can you use them, can we choose the tools that we're going to use for cracking a specific hash list or password, if we're going to talk about live logins. So essentially, we're talking about efficiency. And one of the key points about efficiency is to try not to repeat ourselves, which is a very common issue when we try to crack passwords, because if we're trying to use random word lists from online, we're eventually going to have repeated words in those word lists, or even have words that don't mean anything for our case. For example, if we're trying to hash a password for somewhere where the required minimum number of characters is 6, and our word list has like 10,000 words of 4 characters, we're essentially losing time. So the main objective is to address this problem and try to, within the process itself, try to remove the other side, eliminate what it's not the password, what I'm pretty sure that cannot be the password. So going deeper in the concept of not repeating ourselves, we're talking about repeating the same word from different word lists a lot of the time. It takes time. Separating word lists by length is a very common trick that we can go around this issue, so that we make sure that our word lists are tackled for a specific case. Removing duplicates is another. There's a lot of tools that we can use to address this problem. And then we go over another aspect, which is the information about the hashes, or the place where we took the hashes or the passwords, and the restrictions, and if we're talking about with one or more hash. This is often not. Usually, people don't remind us a small detail like this, like where did I take? Am I cracking one or more hashes? But if we're talking about a group of people that likes fishes, for example, or if we're talking about cracking hashes from a domain which is from a medical enterprise, for example, those people will choose passwords, most probably will choose passwords around the topics that they are more familiar, and usually choose character sets around those topics. So essentially, even if they are not using a word as a password, the words they will choose, by experience, I would say that most cases the letters they choose will have something in common with their interests, essentially. So another aspect of this is the personal information. Interests, native languages, blogs if he has any, and the websites he visits. This tells a lot about our information, and this is one of the reasons why I usually say that you don't need any type of backdoor to get into someone else's phone these days. Okay? Kids these days all post all the time pictures of what they ate, what they like, where they see, what places they like to visit. So you have plenty of information to get into someone else's device easily without any problem. The restrictions is another edge case. This will help us identify we will be pretty sure that it's not a password. Okay? It's an efficient way to reduce the number of word lists that we're going to use, and it's also a very efficient way to reduce the number of permutations that we're going to use in our tools, either those being by the generators or the password character itself. The source, as I said before, it's also important because we can use that source to generate word lists, and we can also use that information, use the source information to try to get more information about the people behind the hashes, if we have any. A single hash is usually more difficult to crack because we have less information to go on. If we have a common interest, we can drill down those interests and try to tackle those problems first, and then as we go, we'll probably save time by finding out that that person's email, for example, is around several forums, and extract that information. We'll be sure that we are somewhere around the interests of that person. So blogs and Twitter, for example, are one of the most used resources to generate word lists for that. Contact information is something that I've found interesting because most people are trying or using something from their contact information to generate passwords or to use them as the numbers they choose to introduce in their passwords, which is interesting. Personal information is another aspect that I found. Some people are using fiscal ID numbers in their passwords, which is interesting. Because even if we are thinking that that's some private information, we need to remind ourselves that every time we ask for a ticket in a store these days in Portugal, we're always leaving that number inside a POS, and that POS is frequently connected to an open Wi-Fi network, so it's not private anymore. Around this research, I found a website which was kind enough to provide me with information like this. So they had, among the pages that they have, they had a user list page where they listed the entire profile of the person. And they forgot to exclude the password hash. This was indexed by Google until a few months ago. So I was probably not the only one to use this, as I said. So taking this, we can apply the information that I talked about previously and try to build a step-based process. So step one, identify the hash algorithm, where you know that it's MT5, identify the source, it's a Portuguese university, and create a word list based on this. So create a word list from the source and create a word list from the user information. And you probably noticed that we have a lot of information from those users. We have emails, the institution where they originally belong, and stuff like that. Tools. I won't go too deep about these tools. Tools are, if you have SSD, for example, I've had good results with rainbow tables. They helped me a lot to eliminate cases where I was trying to figure out if I had passwords that were essentially number-based or full lowercase-based, for example, and had pretty good results. Having a lot of machines also helped in my research because I could run these stacks in parallel and compare results. If you have GPU, if you are constrained by you have time constraint or doing this during an engagement, a GPU is probably a good option, which is probably the reason why I did this in the first place. It's also a good idea to ask Google what he knows about the hash, because as the number of websites are showing up with hashes and cracking hashes and word lists and all that, it's frequently that we don't need to spend any time. Just take the hash, paste it on Google, and it probably knows the password. The tools I used for this was essentially Hashcat and OCO Hashcat, which is the GPU-based tool. And I have a tweaked version of John the Ripper, which is a password cracker with OpenCL, with an OpenCL feature. One of the main advantages of tools like Hashcat is the possibility of using masks. I'll explain a bit more what this is in a bit. The GPU and the fact that we can use multi-core is also important, but this helps us to tackle the word permutation problem. This is an example. For example, if we don't know any restrictions of the password, for example, and we are using GPU, we can use the first case where I'm trying to search for all the lower and uppercase passwords between 2 and 8, and this on my GPU took essentially an hour, okay, to complete all the permutation. So if I take this and drive a parallel with what we said before, what we are doing here, we're eliminating all my word lists that essentially go from 2 to 8 characters within that character set, and we're removing them from the further testing. So I will be pretty sure that in those word lists, I don't have any passwords. But we can use it in a different way. Another case is from between 2 and 9. It took me about a minute, and it can eliminate all the number-based passwords within this range, and so on. So essentially, the brute force, the GPU-based brute force is a good way to address the time problem when we're dealing with unsafe passwords. Anything between 2 and 8, upper or lower case, and even when you're talking about numbers, we can reduce the number of hours if we address techniques like this, for example. The way people memorize a password, it's usually a curious aspect because we're trying to memorize something that is supposed to be hard to guess. And this by itself is a conflict of interest. Okay? I'm trying to figure out a difficult word, but I need to know a way to remember it. So our mind will create a pattern of some kind that we will later try to address it in order to remember it. Some people try to use mnemonics on the way they put their hands on the keyboard, which was a challenge me and my friends had a few years ago, which was trying to guess what someone was trying to type on the keyboard just by looking at it. When we're trying to remember a password, we're usually trying to use the first letter as an uppercase and with two numbers, which will probably be numbers that of our choice, which has usually the last numbers that we saw, the numbers that we usually see because we tell our phone number a lot, so those numbers will probably show up a lot. And those kinds of tricks that our mind plays us in order to remember stuff. So if we try to take this into a parallel, we'll try to build a mask that starts with an uppercase, has a lowercase in the middle, and ends with the two numbers. Or we can reverse it and end with an uppercase, start with two numbers, and try to figure out a few masks around these problems and try to figure out a number of passwords around these. Based on this step, these were the passwords that I found. So the Ds mean it's a digit, the the L means that it's a lowercase letter, the up it's a uppercase letter, and so on. So we have a few people in the last two, for example, the only digits last two were two fiscal IDs. Well, I'm not sure they're all fiscal IDs, but they compute as a valid fiscal IDs. I use the algorithm, validation algorithm, and they are valid, so I would assume that it's not a coincidence. Sports teams, personal numbers, and a few random numbers that I couldn't find any direct logic to were used in this case. We're still addressing words, but pretty short. This took about a minute or two to get the first results. And this leads us to step 2. So by this step, we're completely eliminated the first case, where we have something between 2 and 8, and are usually easy to guess. I have a 2-meter long board at home. I don't know if you guys can see from there what is written there, but essentially what I'm trying to do is a combination map. I'm using the passwords that we already found. I'm addressing the number of different characters that the passwords have. For example, everything from 7 characters have at least, for example, 5 lowercase, and we're trying to deal with those differences. Something from 5 to 7 or 3 to 8. I usually reverse things a bit. And then try to see and match the combinations that I found with the passwords that I found, and try to find out gaps between between the things that I found and the things that I haven't tried yet. So in order to avoid to repeat myself. So I know that I have tried, for example, on the third row. I know that I already tried 1 uppercase, 3 lowercase, and 4 digits. So I can expand that, matching the size of that password. I already know that anything between 1 and 8 digits, it's not going to find anything. So I'm eliminating those cases from the equations and trying to figure out new masks to reduce the number of permutations to build new brute force attacks. Combining this, and in step 2, I found these 3 hashes. We're talking about here of passwords between 11 and 13 characters long. In this case, we're still attacking simple passwords, meaning we're only using lowercase, uppercase, and digits, which is pretty simple to find out. And we're dealing with a single permutation around the uppercase letters. They usually match that information. Although this was a brute force attack. When I analyzed the information, I noticed that we were talking about initials from the names, mobile phone numbers, colors, and fruits, and random numbers that I couldn't find out any reason for them based on the information I had. So this goes even further when we reach this point. When we reach this point, we're trying to figure out passwords between the 10 range and everything else. And this starts to build up, the number of permutations start to grow exponentially. So we need to figure out a way to eliminate all those cases where I'm pretty sure that it's not going to be a password, or those cases where I know that it's going to take a hell of a long time and I don't want to go there. With that, we can use something like this. There are tools online that do this automatically. I like them to do by hand because they help me think. But there are a lot of tools that do this automatically, and you can do statistics about the passwords that you found, and their masks and their computations, and things like that. So when here we're matching the numbers, the masks that I have with the time that they took to run fully. So anything but with 8 characters, talking about on lowercase and digits, took me 31 minutes. Anything with the 3 cases between 2 and 8 took me something that I didn't put there, and so on. Then we start going towards the hours case, where you're going to try to go even further than the 2 and the 9 range digits. It's just somehow people think that a big number is difficult to guess. And then go towards the cases where we're trying to figure out passwords that use dates, for example, of years, where it's going to add or sum word list, for example, with a mask of numbers, making sure that we're trying to guess all the passwords that are using years, special years, or dates, and stuff that we don't have as a personal information. So pattern identification and the collection of word lists is very important. The removal of the what's not a password is relevant in this case, because from this point onwards, we're going to combine things. So I'm going to try to address something that will eventually hit a password where someone is going to use a none, for example, a word, and then a year, or is going to try to use 2 words separated by a number, or 2 words separated by a symbol. And we can address this easily by combining word lists with 2 digit, with the 2 characters, and then 5 characters, and then use a mask on top of it. So by this point, you'll probably guess most of the passwords of your target. You're probably towards the end. And since I'm one of those guys that only either I get 100%, or I don't even bother doing it anything, I took a break. Because who wants to crack a hash list and then realize that it's not possible to crack the last one? That doesn't make any sense. I need to know that password. Word permutation. This is a clever way to tell your kid why he needs to pay attention to math. I was one of those kids that didn't understand most of why I had to understand most of the stuff around those things. But as soon as I started working, it hit me hard. So the permutation problem is a problem, but it's only a problem that it's constrained by time. So processing time grows as time goes. So you're only limited by time in order to solve that problem. So if you're patient enough, you can save a bit of time, take your time, and then wait for the best time to attack this. Or you can try to figure out a clever way to address it. These are some of the tools that I used within this case. The HTTS Gen, for example, is a very useful tool. It's very clever. It uses Markov attack, which is something that I'm not even going to try to explain. But essentially, you can take, for example, a website that I took, for example, was they had an entire Portuguese dictionary separated by size and the first letters. So all the letters with 2 digits started by A, B, C, and goes until the 13 characters. So I did a small crawler, downloaded all the words, and I feeded those word lists to this application, and it created a file. That file is then used by another tool, which is the stats processor, for example, when you can use to generate easy to remember passwords like. Okay, something that it's going to be pretty close to a word, but it's not really a word. Either numbers are exchanged by words or symbols or stuff like that. So you can generate something that usually people choose as a strong password to find out. Another useful tool is the split chain, which helps us to separate words by length. There are others here. With this case, I built a tool that cleans up word lists. It's on GitHub. If anyone wants, I can share it later. But essentially, the candidates were trying to address the permutation problem again and try to use the information that we already have. And that includes the passwords that we already cracked. As I said before, when we're trying to find out passwords from a specific group or that are tackled within a group of people, they're probably going to choose the same things, around the same topics. So we can use those to find the remaining. And I don't know if you noticed, but between the last steps, we're constantly hitting the same things. Personal information, colors and fruits and random numbers thrown in here. And up until now, and I believe that I didn't find any, no one is using some special characters in here. Well, at least no one is using sport teams. This is where things go what I call the full blast stalker mode, which means that you're essentially hit a point where you need to know a lot of personal information in order to know what you're going to be removing as a password. And that means you need to know what the age of that person, for example, his occupation, what he did, his hobbies, how much time he spends online, so his web footprint is important, and the people around his circle of trust. If you don't know, a circle of trust is well, probably should know what a circle of trust is, but it's something that the people that are, if you try to drive this into the personal level, you can say that the people that are closer to you, where you have something in common, are probably going to be your circle of trust. It doesn't mean that you're going to address them directly. It means that you're probably going to use them to get a bit more information about how that person thinks, or what are the topics that he talks about more, in order to know where the sources you're going to, which sources are going to use to generate word lists. His occupation and age is also important, because as we grow old, our memory tries to play tricks with us. So a few years ago, I could easily memorize 20 passwords with 20 characters or more, and these days, not so much. So the last password, which bugged me for a while, between trying to figure out the information that I required in order to reduce the number of permutations, and the attack itself went over a few days. But the brute force itself took only a few hours. So this was one of those cases where I wake up in the morning, put things to run, and only look at it 16 hours later to see if anything showed up. And it turns out that it took only a few hours. I believe it was 2 or 1 hour and a half, or something like that, to find the password. The curious thing about this is something that I've trying to figure out lately, which is something more connected to the psychological level. So all the information, nothing in the password was a word. It's by itself, but all the numbers in all, with an exception of 1 or 2 numbers, all the numbers and all the letters in the password were in his full name, not sequentially, randomly, but they were on his full name. Since this was an academic website, I can figure out that he's probably writing his name a lot. So I can speculate that the words he chose are probably involuntary, but connected somehow to the words that he sees most during his day in work. And a few random numbers, which I couldn't find any direct correlation on his word, on the information I had. But when I finished, I knew probably what was his kids, how many he had, where he worked, his blogs, his Twitter account, and last meals, which people like to tweet a lot these days. Yeah, it's usually very useful. So essentially, what we're talking about here in terms of strong passwords is usually important to address how we're trying to compose our passwords. Using symbols it's a good idea. It's not only a good idea, it should be mandatory. One of the problems that I usually driven a lot is the limitation on the number of characters that the password has. I went through a few websites where 16 somehow is the maximum number of length of a password that anyone can have. I don't know why. but it's important not just the size, but the complexity of the password that we are using and the layers and what we are using to compose that. If we're using something that it's only on our name, we are thinking about something truly random, which usually leads us to use a tool to generate those passwords, which is somehow a better way depending on how you set up. So probably went too fast. No? Yeah. So any questions?
Yeah, go ahead.
I don't have a question. This method assumes this method assumes that there are no delay penalties for the passwords, or is it efficient enough that the penalties does not become an issue?
Sorry, didn't understand. You can say in Portuguese. The slides.
Estes métodos que indicaste, eles assumem, acredito que não há penalidades de tempo para passwords erradas ou são de alguma maneira diferentes que as penalidades não.
Okay. In this example, I'm tackling an offline attack. Okay. So your question is if you're going online, if you're going to incorrect attempts, what the impact is in terms of guessing. In here, I was only interested in an offline attack, so I downloaded hashes and tried to figure out an efficient way to reduce the time required to guess all the passwords. But the online is true. Well, if you have something and you're trying to tackle an online attack, you're not going to use a step mode. You're probably going to do a longer preparation, set up the word list, a better word list, and then tackle the problem directly. Blind brute force, even with masks, on an online attack is probably an insane thing to do because you're going to be blocked easily, and the chances of finding anything it's close to zero.
How difficult would this work become if the hash had salt?
Well, if I didn't know the salt, it would be pretty difficult. It depends on the size of the salt, though. If you're generating the salt, and if you get, for example, to explain that with an example, it's easier. For example, if you're a user, then if you don't have any restrictions to the size of the password from users, and you're salting with 3 or 4 characters, random, those being symbols, lowercase, uppercase, doesn't matter, and the user uses a small and easy to guess password, I'm probably going to step over that password once I tackle the mask attack with a brute force attack. And if I find enough passwords to address a pattern where I think that the salt is only 4 characters only or 8 characters long, I already know that that password is probably salt because if I have a word and then random characters, I can assume that that doesn't belong there. It doesn't make any sense. So you're going to address that by knowing that anything you try, you will need to add that something to match that combination in order to find the other passwords. So it's important not only to include the salt, but design your database or whatever you're storing that information in such a way where it makes it more difficult for someone to extract it in a single shot attack because you're buying time. But it's also important to address the size and the password complexity problem. Because if what you're trying to do there is you're trying to buy time in order to reduce the probability of someone in an offline attack trying to find out how you're going to generate the salt. But there are algorithms that generate the salt dynamically, which is usually the best way to do it.
But that would be even worse in performance, right?
Yeah, you'll have a performance penalty. We're always trading off, but lately in security, we're trading off performance with security. If you take a look, anti-rob chaining, for example, is going to make applications run slower. But
I was trying, the process from discovering the password would be even slower.
It's true, but on the generator itself, it will also have a penalty.
Yeah, I know.
It's usually the reason why most people haven't yet migrated to some of the later algorithms. Anything else?
Hi. So I'm going to ask you a different question from a different angle. So I have several private projects and I program some websites. And I have to think about what would an attacker do to my website and how to compromise the passwords. So I have to decide which criteria I choose to avoid that users choose easy passwords. One of the things I've tried recently was I actually incorporated a word list. I chose a Portuguese word list, which was adequate, and I chose also keywords based on my website. And I compiled it, I also chose some common worldwide passwords. I compiled it all, and I did a matching algorithm. Do you think this is overkill?
And the only problem with the method you're describing is escalation. But the easy to know passwords that word list will continue to grow as long as we'll have IT. So one of the ways that I can recommend you to do is to use something close to the HCA stat, that small application that generates a file. Yeah, it's essentially an anagram. What we're trying to figure out is to match someone's password or choice as a password with a mask and try to see if that mask corresponds to a weak password. If it's only using lowercase letters, if it's only using characters or numbers at the end or at the beginning, or it's grouping things in like 2 digits, 2 letters, 1 number, 2 letters, 1 number, and stuff like that. So those kind of tools will be easier to incorporate into an application and to eliminate the word list or the bad password word list, which I don't really agree with.
Okay. It's just that I thought of some simple examples where you choose one of the words from the word list and just add like 1, 2, 3, 4. And you had a big password, which I actually not secure at all.
Yeah, but those you can get with a mask.
Yeah.
So the mask thing, it's probably one of the easier ways to address the implementation problem and the offline attack. And the source is online, it's on GitHub as well. So the tool, how Markov chains work, which is essentially a math algorithm, it's there, it's implemented in C, which is fairly easy to understand. So you can poke around and figure out a clever way to address that problem.
Thanks.
No problem.
Any more questions? I have one. What will be the next steps for the project when it's open?
Well, I'm currently working on a tool that cleans up word lists. I'm trying to. I was trying to figure out something around what he said, actually. Just trying to come up with a way to create something which tells someone what a weak password is instead of relying on word lists. Because people these days are somehow, I've had into a discussion lately with a guy saying that password shouldn't change or expire, which is completely ridiculous. I don't know why anyone would recommend something like that, but they do happen. So if you're not changing the password, it means that you're not even going to figure out that someone found out that password, because logs are extremely easy to get cluttered and a lot of information there. So it's easy to go over something and not notice that login was brute forced and someone got in on the second or third attempt. And then if those don't change, even don't change on top of it, you're probably not going to find out, and it's going to be used for ages until the user is eventually disabled. So the next steps will probably go over those things. Try to come up with something to share to the development side.
Thank you to the
Thank you.